Okay, so just recapping what I was typing in the chat there, which is I will post your final exam questions tonight. And when I say tonight, it might technically be tomorrow because it might not. I might not post them till like 1 or 2 a.m. Um, but you're gonna have until midnight on Sunday, until like 11:59 on Sunday. Is when you're gonna have to finish this. So you got like 5 days basically um, to do it, and it's gonna be a little bit longer than exam two, maybe like I don't know, 50 to 75% longer than exam two. It won't. I mean, it will certainly be within the range of a normal final exam, so roughly about the same length as a normal final exam. So if you look at any of the exams in the test bank, if you really wanted to look beforehand, if you can't wait for a few hours to see what it looks like, the exams in the test bank, the final exams from the test bank for the past few semesters are going to be what I am mostly basing it on. I've written like 90% of the exam. Anyway, so um, well, yeah. The extra lecture video. Yeah, you're not really going to be tested on that stuff because those were purely supplemental anyway. I meant to do it over the weekend, but unfortunately, I wasn't able to fix my computer until like last night. So unfortunately, I was unable to do much of anything until today. So yeah, you're not really getting tested on that stuff. So by the end of by the end of today's lecture, you'll have seen everything you need to know for the exam. I was originally going to kind of spend the entire lecture today going over stuff, but then I decided, well, since I'm gonna post the final exam in a few hours, it didn't really make that much sense to be prepping you as if you were gonna be taking an exam in a class without notes and stuff. So at the end of today's lecture, I'm going to go through like a quick bullet point, just reminding you, especially some of the stuff we did early on in the semester. But you got access to your notes, so it's not like you got to go through a whole thing trying to memorize and like efficiently study the stuff because you're going to have like 5 days to do it. So this should be like a leisurely stroll. Shouldn't be too worried about it. Eigenvectors. How would eigenvectors be graded on the exam? What do I mean? What do you mean? Like the fact that you don't, there's multiple answers. I mean, you're gonna find eigenvectors, and they're not gonna be too ridiculous. Even if they are, the vectors only have two entries, so the TAs when they're grading them will be able to tell the difference between, or will be able to award points the same for the eigenvector 1 1 and the eigenvector 17 17, right? So that's not a problem. I assure you that we are able to deal with the ambiguity that eigenvectors introduce, the fact that they're not unique. Um, so yeah, what was I saying? So yeah, your final exam will be posted, like I said, sometime later tonight, and you'll have about 5 days to do it. Your second MATLAB's due at the same time. There is going to be a MATLAB question on on your final exam, but it's not really a MATLAB question. It's I mean, I don't know that it even deserves to be called a MATLAB question, but it involves MATLAB syntax. But I wouldn't worry too much about it. I think that's about it. Oh, I was asked, do I plan on curving the class? I shouldn't need to curve the class because I believe that's going to take care of itself because I didn't look exactly to see what the average was, but just glancing over the grades looked like the average on on exam 2 was like a 95 or something. Uh, so don't think I'm gonna have to worry too much about a curve because like I said, there's not gonna be no curveballs thrown at you. The final exam is going to be, same like level of difficulty as exam 2, so I expect really high grades on it. So like I said, I don't think I'll need to curve much of anything. I think everybody will do well relatively. So did I miss anything? I don't think so. I think that's everything. Yep. Yep. Okay. So, I mentioned at the very beginning in the chat, and I posted a link to the notes. It'd be easier for everyone when I get to, or just periodically, you should probably look while I'm sketching some of these things as you go along. If you want to see pictures that look better than what I'll draw, you should look in the notes. So the classification of phase portraits involves sketching a bunch of stuff in, like, I guess what are the like 19 main cases, but or really it's like 15 main cases. A lot of the sketches look very similar, and the only thing that's different about them is the direction of the arrows. But at any rate, it's better to look in the notes to get a better picture of what's going on, because my drawing is clearly not going to be as good as a computer rendered drawing. So anyway, that's what I'm going to do. I'm going to finish up this discussion of phase portraits, and then like I said, I thought I would do maybe a little bit of reminder of some of the stuff we've covered, and that will be that. So phase portraits. Like I'd said last time, the idea is I have the following differential equation. So the derivative with respect to t of a vector of unknown functions x and y is equal to a coefficient matrix A times the vector xy, where the notation we're going to use for A is standard matrix notation. So I have entries A11, A12, A21, A22. Okay, so here's my coefficient matrix. And so to draw a phase plane portrait, the ideal was exactly the same as for non-systems, right? First order, when we talked about autonomous equations, drawing phase plane portraits, the idea was exactly the same. We wanted to come up with a way of being able to sketch long-term behavior of solutions. So I mentioned at the end of the last lecture this fact that basically this split into, so we're only going to consider this case when A is a 2x2. Like all of these system problems, to simplify things, you're only going to be considering 2x2s. And so you know that writing out the characteristic polynomial for A is using the usual expression. This is z squared minus the trace of A, z, plus the determinant of A. And I could write all of those in terms of A's entries. I'm not going to do that. I'm just going to leave it like this. The point is that this is a quadratic. Okay, and so the eigenvalues are roots of this thing. And how do the roots of a quadratic occur? So you've heard this a million times in this course by now. The roots of a quadratic come in 3 cases, right? So there are 3 major cases. So major case 1 is 2 distinct real eigenvalues. That's case 1. Case 2, 2 complex conjugate pair eigenvalues. And case 3, 1 real double root. So 1 real double eigenvalue. That is a multiplicity 2 eigenvalue. Okay, so these are the three cases. Okay, so I went through the cases in the first major case, but I'm going to do that again. So case 1, 2 real eigenvalues. So the idea here was we already know what the general solution looks like. So general solution to, what do we want to call this? Let's call this star. So if I call this star, general solution to star is the following. So I can write it as, I know it's a little bit confusing because we used x here, but if I call this entire vector x, as is typical, then this just becomes another way of writing x prime is equal to ax, which is, our usual abbreviated way of writing this equation. So using x bar as my notation here, so the general solution in this case can be written as c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. I'm not going to rewrite this because I've said this a bunch, but lambda 1 v1 is the first eigenpair and lambda 2 v2 is the second eigenpair here, right? Okay, so this is my general solution. And we saw last time that there were 5 main cases that this broke into, and it all depends on the relative size of lambda 1, lambda 2. Okay, so couple of cases, so subcases. There are 5 of these. Okay, so the first one is 1 is positive and 1 is negative. Okay, so I'm not going to write the full description. If you want the full description, it would take me way too long because there's a lot of words. So I wrote out the full description of this, I think, last time in last lecture. So you could have a look at that, or alternatively, you can just look at page 9 in the notes. So this is page 9 in 3.7. That's all of this is 3.7. So page 9 in the notes in 3.7. So everything I talk about today is going to be in 3.7 in the notes. Okay. So page 9 in 3.7 lists all these cases if you want to read exactly the behavior that happens in each case. So here's my first case. I'm just going to write out what this is called. So this is called a saddle. You might recognize that word coming from saddle point if you remember that bit in Calc 3. There was the description of a saddle point, and actually that's more or less what's going on here. It's just in 2D. Instead, you could view this almost like a cross section of a saddle point. So what does this thing look like? The idea is I have a picture. What is this picture showing? This picture is showing the behavior of solutions near the origin. So the point that I'm going to draw in the center is the origin. That's 0, 0. Okay. And there are lines I draw here. Okay. So there's one, there's another. Now, I've drawn them in this case so that they look nice like this. They're not always going to look like this because these lines are associated to eigenvalues, or to eigenvectors. Okay, and so what I get here is the following picture. I get this line. So along this line, solutions get pushed out away from the origin. The origin is what's called a stationary solution, right, or an equilibrium solution for this equation star. And so the origin goes nowhere. The origin is fixed. Okay, so a solution beginning at the origin stays at the origin. Solutions along this line get pushed out. Okay, so just from knowing that little bit, what does that tell you? So if the arrows are indicating a t going to positive infinity direction, then along this line, if solutions are being pushed out away from the origin, what is this line associated to? It has to be associated to V2. Okay, this line has to be associated to V2. So this line is associated to V2. And the reason why is because since lambda 2 is the bigger eigenvalue, then as t goes to positive infinity, that term dominates. Okay, and so it gets pushed off to infinity. Since lambda 1 is the negative eigenvalue, as t goes to positive infinity, that term goes to 0. And so along this line is the line associated with V1, solutions get pushed towards the origin. And that's what these arrows indicate. And now to fill in this picture, if you have solutions that are not along these lines, so these lines, sometimes you'll see them called orbits or eigensolution orbits. That's what the notes call them. So if you have solutions that don't quite do that, well, maybe those pieces of curves look something like this. Okay, so maybe they look something like this, and you can fill in the arrows along these curves in this way. And how do I know in what direction my arrows go? They go in a way that makes the picture consistent. What do I mean consistent? When I fill in that picture, the arrows should match up with the arrows on the lines associated to the eigenvectors. Okay, so what do I mean by that? Well, in order to see how this has to go, what you could do is think of solutions that pass really close to these lines. So imagine your solution gets really close to this line and then turns and is really close to this line. When you see that it's really close, it's almost the same as this line, right? It's almost parallel to it here, and it's very, very close. And those arrows have to be pointing in the same direction. And when it gets here, they have to be pointing in the same direction. And so that is how to tell the direction that these arrows have to go for these solution curves. Okay. Again, I know that this is a very ugly picture. If you want to see a nice picture of this, you can look on the next page. On page 10 in the notes shows an example of this, and it shows nicely labeled what it is that's going on. What are these arrows telling you? They're telling you asymptotic behavior. So it's saying that as t goes to positive infinity, the arrows indicate how these solutions are behaving. So this solution starts here, and as t goes to positive infinity, it is approaching this line associated with V2. Okay, it is being dominated by this second term. That makes sense. This is the larger eigenvalue. Same thing is true as t goes to minus infinity. This solution is, I'm going in the opposite direction of the arrows, so it is going towards the line associated to V1. Okay, the smaller eigenvalue. As t goes to minus infinity, since lambda 1 is negative, this becomes the dominant term. Okay, so that's a full description of what it is that goes on here. And that description basically holds for everything that follows in this first case. So I'm going to quickly go through that. So going through the remainder of these cases. So the second case, so this is subcase, I'll call this 1. So here's the next case. So this is, both of them are negative. So lambda 1 is more negative. Okay, so lambda 1 is more negative. Okay, this is called a nodal sink. Okay, It's called a nodal sink. So in this case, both of these are negative. So as t goes to infinity, what is going to happen? Well, you might imagine, since both of these things are negative, as t goes to infinity, all the solutions are going to 0. But this is a vector valued thing. Going to 0 here, that's going to the 0 vector, but that's the origin, right? So in a nodal sink, all of the solutions are going to the origin. So all solutions go to the origin as t goes to infinity. Oh, that should be. So as t goes to positive infinity, all solutions go to the origin. What does that look like in picture? Well, the idea is I still have these two lines. So I still have the line associated to V2 and the line associated to V1. So that doesn't change. Okay, but then what happens here? So, well, along these lines, everything travels towards the origin. Okay, so along both of those lines, everything travels towards the origin. And no matter how my solution paths begin, they travel to the origin as t goes to infinity. So you'll see the picture looks something like this. Notice the arrows are all pointing in a way that indicates that these solution curves always converge on the origin. They always go to the origin as t goes to infinity. So as t goes to minus infinity, they're going out from the origin. Okay, they're actually doing the opposite of this next case I'm going to talk about. Okay, so the next case, you might imagine, is instead of a nodal sink, it is a nodal source. Okay, now you might have a look at the origin of these names. If you've heard of sink and source before, then it's not too mysterious why these are called this way. So a nodal source actually looks exactly the same as a nodal sink, but the arrows are going the opposite direction. So a nodal source, again, the point in the middle is the origin, and later we're going to talk about stability, and what we mean is talking about stability of the origin as an equilibrium solution. All right, so this is my line for V2, this is my line for V1, and again, the only difference here is the arrows are moving away. So why is that? Because in the nodal source case, just like for nodal sink, I'm in the direct diametrically opposed case where I have two positive eigenvalues. Okay, so two positive eigenvalues. So along these lines associated with the eigensolution terms, right? This term ignoring this, and the second term ignoring the first one. So everything is moving along those lines out, and then the other curves emanate from the origin. And hence it's called a source. Okay, so again, just like in this case, the arrows are just going in the opposite direction. I know my pictures are ugly, that's why I'm referring you to page 10 in the notes. Okay, so those are the first three of those cases. All right, the last two cases happen less frequently, but I'm going to cover them anyway. So case 4, so this is still major case 1, number 4. This is 1 negative and 1 0. Okay. Well, think about what that means for a second. So let me bring it back for a second. So if lambda 1 is negative and lambda 2 is 0, so then this is e to the 0t, so that's just 1. So this is just a constant times vector. So I have an exponential term where lambda 1 is negative, and I'm adding to that exponential term this constant times a vector, but the vector is scalar valued in the, or I shouldn't say that. I should say it is a constant vector, right? So the vector does not depend on t. So what is that? What does that look like? Well, it looks like the following. So I still have my usual picture. So I still have my usual picture. For V1, nothing has changed. Okay, and because lambda 1 is the non-zero eigenvalue and it's negative, then if here's the origin, as t goes to infinity, of course I'm approaching along the origin here. But then what about this line associated to V2? How is it different? Well, notice that, again, going back, because lambda 2 is 0, as t goes to infinity, I'm not approaching the origin along V2. In fact, this is just constant times my vector V2. And so what I actually get are, it looks like translates of this along V2. So what I get is a picture that looks something like this, where along these lines parallel to V1, I get convergence to this line. Okay, but that's all I get. All right, so this is how it goes, and this is, I'm not even going to write that this is associated to V2, but that's how this goes. This is called a spinal sink. Again, this is a rarer thing. It's rare that one of these eigenvalues is 0, but it can definitely happen. So, and that's what it is. So if that's a spinal sink, you might imagine what I'm going to say next. So what if lambda 1 is 0 and lambda 2 is positive? Well, in that case, we have what's called a spinal source, and it's exactly what you expect. It's similar picture, except now I should say that the non-trivial line is the other one, right? So the non-trivial line is this one. So this moves out and away, right? So if this moves in, this moves out and away. Okay. All right. So that is the exhaustive list of cases that can occur in that first two distinct real eigenvalues cases. Okay. So that covers the two distinct. So that's all for the two real eigenvalues case. All right, so going back, I have taken care of this, that split into 5 cases. So moving on to two complex conjugate pair eigenvalues. So two complex eigenvalues. All right. So the notes goes through the trouble of actually writing out what the general form of that solution is using the general form of the matrix exponential. We don't need to refer to that really. All we have to worry about is just if we have eigenvalue pair mu plus minus I nu, there are a couple of cases here. So the main cases are determined by the sign of nu and then an additional thing. Okay, so behavior is determined by two parameters. So I want to remind you, we're looking at the equation x equals a, or x prime equals ax, right? And our notation was a is a11, a12, a21, and a22. Okay. All right. So the parameters in question are mu and either a21 or a12, and I'll explain here in a second. So so the parameters in question are so one, if mu is equal to 0, then what happens? If mu is equal to 0, the eigenvalues are purely imaginary. And in this case, the orbits, the solution curves, are ellipses centered at the origin. So if mu is equal to 0, then all orbits are what we call those solution curves that we're sketching. So if mu is equal to 0, then all orbits are ellipses about the origin. Okay, well, imagine for a second you have an ellipse around the origin. Well, there's two ways that you can travel around that ellipse, right? There's counterclockwise and there's clockwise. So then how do I determine this? So first of all, this is called a center. So this is called a center. Okay. It turns out that the center is clockwise if a21, this entry here in the matrix, the coefficient matrix A, if a21 is strictly less than 0, it's clockwise center, and counterclockwise if a21 is strictly greater than 0. Now, the way that you can remember this, if you were taking this exam without reference of notes, is you use the right hand rule. And if it's positive, if a21 is positive, you imagine your right thumb pointing up out of the page. Fingers indicate counterclockwise rotation. That's how I would have taught you to do it. You don't have to know that now because, well, you're going to have access to your notes. So that's the deal. Now, you're probably already saying, wait, you know very well that for a coefficient matrix, you could definitely have this entry be 0, but I don't account for that. Okay, I don't account for that at all. So if a21 is, what happens if a21 is 0? Well, I can read this off from a12 instead. So I can read this off from a12 instead, but if I read it off from a12, I have to swap the order of these. Okay, so I swap the direction of these. So if a21 turns out to be 0, which doesn't happen very often, but let's say that a21 is 0, I don't have to use a21, I could use a12 instead. Using a12, the opposite of what I said here is true. Okay, and so what's the next question you're going to ask? The next question you're going to ask is, what if a12 is also 0? Well, if a12 is also 0, then your matrix A, being a real matrix, would just be a diagonal matrix. And if it's a diagonal matrix like that, its eigenvalues are just readable from the diagonal, so it would actually have real eigenvalues. So they can't both be 0. We're in the case of two complex eigenvalues. So a21 and a12 can't both be 0. One of them will be non-zero, and you can use that one to determine whether this is clockwise or counterclockwise. So when I say it's determined by two parameters, the first parameter is mu, and the second parameter is a21 or a12. Okay. Once you know that, you can exhaustively write out all these cases. So I'm going to actually write out in words what these are and then do all of the cases in a single picture. So the second possibility, and each of these, I'm going to list three possibilities, and each of those split into two. So you're going to get 6 total cases out of this. So in 2, if mu is less than 0, then all solutions spiral into the origin as t goes to infinity. Okay, so this is a spiral sink. Okay, the spiral is clockwise if A21 is negative, and counterclockwise, I'm going to abbreviate that as CC, if A21 is positive. And lastly, E. If mu is positive, what's going to happen? Then all solutions spiral away from the origin as t goes to infinity. This is called a spiral source. And I'm just going to write similar to above. So clockwise, I'll write it like this so that I don't have to write it fully out. So clockwise or counterclockwise is as above. So whether this spiral source is clockwise or counterclockwise is determined in the exact same way. All right, and so you get 6 possibilities. These are depicted on page 12. So let me turn my sheet here. Actually, I can do it this way. Okay, so this is page 12 of the notes. What does this look like? I get 6 pictures. I'm going to go ahead and draw them out like this. Now, these cases would have been built upon for a slightly more general problem where we can sketch some local behavior of more complicated systems. But unfortunately, due to the situation this semester, we weren't able to get to that material, and so this is going to be the last thing we do with these pictures, essentially, which is still a decent amount of info. Actually, it's good asymptotic info. So in each case, we have the origin in the middle. Okay, that is our fixed point, so that's our equilibrium point that we're trying to say something about the stability of. Okay, and so in the case that we had centers, there was a clockwise center and counterclockwise center. So there was clockwise center and counterclockwise center. And remember, centers were in the case that mu was 0. So mu is 0. If it was clockwise, A21 was negative. And if it was counterclockwise, A21 was positive. So I'm not going to write A21 here since it's the way that it's determined is exactly the same for all of these. But I wanted to at least write it there. So these look like ellipses centered around the origin. So the picture looks identical. You can't tell the difference until I slap arrows on them. Since it's clockwise center, the arrows go like this. Here, since this is a counterclockwise center, the arrows go in the opposite direction. Okay. Same thing for the spiral sinks and spiral sources. So here, maybe I want to do it like this. Okay. So for a spiral sink, they're all going towards the origin, and they're doing it in a way that is clockwise here. So this is a clockwise spiral sink. So the spiral sink bit is mu being negative, and here's a counterclockwise spiral sink. So this is still mu being negative, but A21 is positive here and A21 is negative here. So that's how this goes. And here's what it looks like. There's a clockwise spiral sink. A counterclockwise spiral sink looks similar. It's just that my arrows go the other direction. Right. Okay. And lastly, I have clockwise spiral source and counterclockwise spiral source. So in both cases, mu is positive. In this case, A21 is negative. In this case, A21 is positive. So what do these look like? Well, see, these are very fun to draw. The arrows are going out, right? They're going out and away from the origin, but they're doing it in a clockwise manner. Okay. So I know that it can be a little confusing, especially when you first start drawing these, because you draw them and your arrows are going in the right direction for the clockwise portion, but oh wait, they're going towards the center. They're going toward the origin, so it's a sink instead of a source, right? That's kind of the annoying thing about these. So it takes some practice to get used to drawing these going in the right direction. So again, the arrows need to point out, but here they need to be counterclockwise. Right. Okay. And that's all of the cases. We'll be posting PDF and MATLAB problems on Elm so we can confirm the correct ones. Yeah, I could do that later when I post final exam. I'll just take pictures of the problems that I assigned. I think, like I said, I think I checked, and I think that the issue was like the page numbers were off, but I didn't reference any page numbers this time. So I think all the problems I referenced are the right ones. They're not going to be on the same pages as they are in the e-copy, like the like newest electronic version. But I believe all the numbers should be the same. But I'll like I said, I'll post it anyway, just in case. That's not a big deal. Even if you end up doing the wrong ones, that's not a big deal. Okay. So then, this is the 6 cases that the complex eigenvalue splits into. So going back here, we're almost finished. So that's our 2 complex conjugate pair eigenvalues here. So I have to finish up with 1 real double eigenvalue. So these are actually not nearly as interesting. So there's radial sinks and radial sources. That's a really simple example. So so in case 3, one case is that A is equal to mu times the identity, i.e. your matrix is actually mu 0 0 mu for some real number mu. Okay. Well, in this case, you get 2 possibilities. you get what's called a radial sink or a radial source. So again, here's my origin in the middle. A radial sink is everything converges on the origin by lines in this nice way. You can see why it's called radial here. But oh look, it's all going towards the origin, so it's a sink. And this happens exactly when you expect. It's when mu is negative. You get a radial source when mu is positive. So same idea. It's just that the arrows go in the opposite direction. Okay. So this doesn't happen very often. I should say happens very rarely. I mean, this is, you could see, I mean, this literally, your coefficient matrix is a multiple of the identity. This is a really, really simple and special thing. So then, what is the other subcase? So here's the other case, and this is A is not a multiple of the identity, and A has a double eigenvalue, mu. So, or maybe to not confuse you, lambda is mu. So it has a single double eigenvalue called mu. Okay. So this actually works kind of, sort of similarly to the complex case. So there are shears. I'm not going to draw those. These are on page 14 in the textbook. So shears are what you get when mu is equal to 0. And whether or not you get a clockwise or counterclockwise shear, they're called clockwise and counterclockwise, but you'll see if you look at them in the notes, they don't really look that way. But that is what they're called. They're called shears. You can see why they're called shears, because you have a stationary line passing through the origin, and then the orbits, the solutions, are like parallel translates of that line essentially, and they're going, well, you see how they're going. They are think of it as dividing the plane into the upper half plane and the lower half plane. Follow the trajectory of the arrows. You are shearing the top and bottom, right? You're essentially moving them in opposite directions. Same thing for the counterclockwise shear. So the more interesting ones are when mu is negative or mu is positive. So the shears, like I said, you can look on page 14. So when mu is negative, in this case, you get what are called twist sinks. Okay. So what does a twist sink look like? So one thing about this case is it is really like a blend of what happens. It's like a blend between the first two large cases. Notice that in all of these pictures, there is no line jutting through the origin. Remember where that line came from, or where the lines came from. Each line in the previous case was associated to an eigenvector, right? So there's the first three cases we talked about for two real eigenvalues. And here's the other. There were lines jutting through the origin, and the idea is those lines were associated to real eigenvectors. Well, in the complex case, there are no real eigenvectors in that way. And so there are no lines dividing the plane in this way. Okay. And so in the complex case, we don't get those lines, right? We got two of those orbit lines, those eigenlines, in the two real eigenvalue case. So in this case, we get one. Okay, we get one line that's associated to the single eigenvector that I get for mu, right? And so since it's a sinc, mu less than 0, you can imagine if here's my origin, then along this line associated with that eigenvector, I'm moving towards the origin as t goes to infinity. But then I don't have the other line. Remember, one way of thinking about phase portraits, even in the old case at the very beginning of the semester, one way of thinking about phase portraits was due to the existence and uniqueness theorem. It said that these solutions can't cross each other, right? And so essentially these lines I'm drawing in erect like a barrier that can't be crossed by other solutions because it violates uniqueness. Okay. And so it can only be crossed at infinity. So that's why like they can touch each other here at the origin as t goes to infinity, but if t is some finite value, they can't cross or touch each other. Okay, so yeah, as t goes to infinity, they can touch, or as t goes to minus infinity, they can touch, but they can't cross each other like out here. And so that doesn't happen here because there are none of those lines. And so these are free to do things like spiral around, right? They can't do this motion. If there was a line jutting through that origin, they wouldn't be able to spiral in this way because it would cross the line and that'd be no good. But notice what happens here. Here there's a single line. There's not two, there's just this one. So then what happens is you get something like this. So you get something like this. Okay. So they are kind of sort of like spiraling in toward the origin, but they can't quite spiral like a true spiral because that would be crossing this line. So they do something, like this. I did a pretty bad job of drawing it. It's better if you look at the picture in the notes. It's page 15 in the notes. But a twist sinc looks like that. And of course, exactly the same is true. This is true if A21 is negative or A12 is positive. And so this is a clockwise twist sinc and a counterclockwise twist sinc, which is exactly, again, as you imagine it. Here's my line. It's being approached. It's still a sinc. And it's still sinc because the arrows are still going towards the origin as t goes to infinity. Okay. All right, so here's my, again, mu is still negative, and A21 is positive, or A12 is negative. And then lastly, mu greater than 0, there are twist sources. Okay, I'm actually not going to draw those. They look exactly like this. It's just the arrows go out instead. So the arrows go away from the origin. Instead, and twist sources happen when mu is positive. And the same conditions on clockwise versus counterclockwise holds. Okay. So that is the completely exhaustive list of cases here. One last thing I wanted to mention before I give you like a quick rundown. So there is a very long summary that you can find on pages 16 and 17, but especially pages 16. So long summary on page 16. The last thing I wanted to draw your attention to is classifying stability. So there's something called the mean discriminant plane. I'm not going to get into that. It's a really nice way uh, of having a picture that totally classifies the the cases in terms of like a really nice picture with a parabola, and it shows exactly where each of the things occurs in that mean discriminant plane. Um, but you don't need to have a look at that. It's interesting. You should have a look at it if you're interested, but you don't need to. So the main thing I wanted to talk about was stability, or the last thing I wanted to say was stability of the origin. So and I don't need to write anything here because well, maybe I should, even though this is on. So this is page 20 in the same section. So to talk about stability of the origin, there's a couple of definitions. So first definition, um, so we say the origin is stable if every solution that starts sufficiently near the origin will stay arbitrarily close to the origin. So if every solution that starts sufficiently near the origin will stay arbitrarily close to the origin. Okay. It's unstable if it's not stable. Okay, so it's unstable if it's not stable. One more definition. We say that the origin is attracting if every solution that starts near it will approach it as t goes to infinity. And we say that it's repelling if every solution that starts near it but not at it will move away from it. So we'll move away as t goes to infinity. Okay, so very descriptive definitions here. You might immediately see that there's got to be some relationship between these things. In fact, stable and attracting sound very, very similar. Um, but it turns out attracting is actually stronger than stable, because stable allows for things like centers, right? So stable allows for things that are solutions that are, centered at the origin in the complex case, just going around the origin very close to it. This would be stable because it's staying near it. It started near the origin, it's staying near it. Attracting is a little stronger because it requires not just that something that stays near it is still near it as t goes to infinity. It actually has to approach it. It has to go to 0 as t goes to infinity. So attracting is a stronger thing than stable. Similarly, repelling is a stronger thing than unstable. Okay, and so there is a list. This is also on page 20. I'll go ahead and write it out here just so you can see it in the video without having to refer to your notes if you prefer that. So the table. So there's attracting. First of all, attracting implies stable. The converse is not true. Okay, repelling implies unstable. The converse is not true. Okay, So there's attracting types, stable, so attracting and thus also stable. So this is also stable. They're stable but not attracting. There's unstable but not repelling. And there's repelling, which means it's definitely unstable. Thus also unstable. So this is at the bottom of page 20. So what are the attracting cases? Nodal sinks are attracting. Radial sinks are attracting. Twist sinks are attracting. And spiral sinks are attracting. Wow. Amazing. It's very surprising, right? Okay, just from the behavior alone, the description of those definitions alone tells you exactly what you expect here. So then what about stable but not attracting? Well, the centers, as I mentioned, centers are stable and not attracting. Notice, again, as I want to stress, all these are stable because they're attracting. Attracting is stronger than stable. So all these are definitely stable. But here's the list of stable but not attracting. So centers are stable but not attracting. Spinal sinks are stable and not attracting. You should look at the pictures of these if you're confused about why they fit into these categories. Null, I didn't even talk about null. I'm not even going to put it down. Yeah, I'm not even going to put it down. You can look up the null case. It's not going to happen. Spoiler. So you don't really need to even think about it, but it's literally the trivial case. So unstable but not repelling. These are saddles. Are unstable, but they're not repelling. Remember, along one of those lines, they're actually attracting. Okay, so the thing about a saddle is it's attracting along one of those lines and it's repelling along the other. So that's unstable, but it's actually not repelling. There's spinal sources and there's shears. Okay, not having null here means there's a little bit of like asymmetry, but that's okay. And then what do you think are repelling? Well, it's all these except instead of sinks, it's sources. So nodal sources, radial sources, twist sources, and spiral sources. Okay. And so, on your final exam, maybe you will be asked to classify the stability of the origin. How would you do it? Well, you would do this analysis exactly as we did here, and then you'd say, okay, what did I end up with? Oh, well, okay, I ended up with a radial sink, so it's attracting. Right? Or, oh, I ended up with a saddle, so it's unstable, but it's not repelling. Okay, so that's the idea here. Yes, that's exactly what these phase portraits give. So just like earlier in the semester where we drew some candidate solution curves using the phase portrait, that's what's going on here. You are drawing some potential solutions, what a solution curve could look like for that equation. And so to actually pick out one of those, of course, you would need initial conditions, but that's exactly what you're doing. You're looking at the end behavior in that way. Okay, so quick rundown. Of course, the material that we've done splits into three main pieces, right? So there's the first order stuff. So in the first order stuff, what did we do? So there was the stuff we did from the recipe, right? So recipe for first order linear. So if you had a first order linear equation, there was just literally a recipe. This is the integrating factor business, right? So whatever form you remembered it in, integrating factor was the recipe for the first order linear. There were separable equations, right? Separable equations could actually be, separable equations could actually be non-linear, but you could still solve some of them even explicitly. So you should know how to do that. What else did we do? We did phase portraits for autonomous. So phase portraits for autonomous equations. What else did we do? We did tank problems. Okay, what else did we do? We did exact and integrating factor for exact differential forms. There was the basic numerical stuff we did, so Euler's method. Okay. When it comes to solving for any of these, of course, there was general terminology surrounding, so finding unique solution to IVPs. And intervals of definition, that's something that's not just a first order thing, and intervals of definition. So this was something you've done throughout the course, not just for first orders. That's a pretty good list for first order stuff. You guys had to know how to do. Okay, but in terms of solving, of course, some of these might only have an implicit solution. If that's as good as you can do, that would be said on the exam. So if as good as you can do is the implicit solution, I would say find an implicit general solution to the equation in question. There was part 2, which was called higher order, and technically we did have some theoretical, like theory stuff that was done for higher order stuff. So say higher order, because like I said, there are some questions you can answer that are technically about higher order differential equations. Really, of course, the focus was on second order. Okay. So, 1 is general theory. What do I mean by that? Refer to problem 1 on exam 2. So problem 1 on exam 2 gave you a list of roots of the characteristic polynomial and asks you a bunch of questions about the equation it came from, right? The order of the equation and how to construct a general solution, right? So things that fit into general theory is understanding what the Wronskian tells you, understanding how to come up with the homogeneous recipe. So I might as well rewrite that. Of course, you should know, should be burned into your soul by now, the homogeneous recipe for the solution to the homogeneous constant coefficient second order equation. Okay. 3, non-homogeneous second order linear constant coefficient equation. Okay, whether by key identities or undetermined coefficients, finding the particular solution, knowing that the general solution to this is homogeneous part plus particular solution. That's obviously a very big part of this course. So then after that, and of course this took us a long time to do. There's a lot of material there, even though that's really all we were doing there. Um, so then for variable coefficient stuff, which really means variation of parameters. Okay, so variation of parameters. Green's functions, you can definitely look at that all you want to, but I'm not going to ask you specifically to do anything via Green's functions. That doesn't mean you can't use them. You definitely could use Green's functions to do some of the final exam problems, but you don't have to. I'm not going to ask you to do that. It's not going to make your life easier. Okay, next, spring problems. Okay, so those application problems where I gave you some spring mass system and you had to derive the equation that governed it and answer a few questions about it. That sort of stuff, of course, is fair game. Basically anything from exam 2 obviously is fair game. So Laplace transforms. This also includes questions where I might not even give you an equation. I might just literally give you a function of S and say, this is the Laplace transform of the solution. Tell me what the solution is. Right? So literally, I might just give you a problem that has you computing inverse Laplace transforms. Typically, in this class, the final exam includes a Laplace transform table. That's not necessary for you guys since you're allowed to use your notes, so have at it. There's any number of Laplace transform tables in the notes you want to look at. Is that everything for second order? I believe it is. I think that's everything. Okay. And lastly, the last thing you got to know is this. So this is linear systems. So one, you got to know how to solve x prime equals ax via eigenmethods. Got to know the fundamental matrix. C of t. Got to know its relationship to matrix exponentials. That was a very quick bit of lecture. So matrix exponentials, e to the ta or e to the at, however you want to write this. This is c of t times c of 0 inverse. That was all you needed to know once you'd done this via eigenmethods. So a is going to be a 2 by 2 here. And when I say, of course, do this via eigenmethods, that includes the entire process. You got to know how to find the characteristic polynomial of a matrix and how to solve it for the eigenvalues, how to find the eigenvectors, how to fully solve this for its general equation using eigenmethods. Okay, so you need to know fundamental matrix, matrix exponential. So when I say solving, I mean finding the general solution, right? So find general solution. Or find explicit unique solution to some matrix IVP. Okay. And then lastly, sketch phase plane portraits of, again, x prime equals ax. And included in that, but I'll list it as 5, is classify stability of the origin. Okay, using that terminology we did at the very end. All right. Well, that is that. That is what you need. That is what you all learned in this course. So that's it. So I will post that later tonight. Like I said, don't freak out too much if it's not posted by like midnight. it'll be posted, and you have until midnight this Sunday to finish it. Um, so that's it for the material. You've learned everything you're going to learn in this class. So hopefully it wasn't too painful with the move to online. Certainly not ideal, given that this was meant to be, obviously, these lectures are meant to be delivered in person. So it has been an experience, but you shouldn't worry too bad. This is, it's not going to. I will try to do my best to make sure, that you all suffer minimally on account of the situation that you didn't have anything to do with. So anyway, that's the semester. So I'll be around. Pay attention to announcements, like I said, when I announce those things. Since I'm posting the exam tonight, I'm not going to have like review sessions or anything. You guys are just going to get to it. So that's it as far as our recorded lectures and all that goes. So I have fun doing the final exam, and have a good summer, and a good, maybe you'll have me in a class later in the fall, or later, whenever, if you want to take more math stuff. I teach a lot of different math, so a lot of options there. But anyway, all right, take care, everyone. Like I said, I'll post it sometime later tonight, so keep a lookout.